Picture this: a cold, silent expanse stretching farther than the human mind can grasp. Then, in an instant, a burst of light and sound shatters the stillness as a rocket tears through the sky, carrying with it the hopes of an entire species. That moment, and so many like it, didn't just happen in isolation, they rewrote history itself. From the first time humanity left Earth's atmosphere to the echoes of distant planets calling us toward the unknown, space exploration has been more than a series of missions. It's been a mirror reflecting our boldest dreams, our fiercest rivalries, and our unshakable determination to reach beyond what we thought possible. Think about how different your life would be without the technology born from these milestones. No satellite navigation, no weather forecasts pinpointing storms days in advance, no glimpse of Earth as a fragile blue marble hanging in the void. These aren't just scientific achievements, they're cultural earthquakes that shifted how we see ourselves and our place in the cosmos. Every launch, every discovery, every heartbeat skipped in mission control was a thread woven into the fabric of human progress. Some moments were triumphs that united nations, others were tragedies that reminded us of the cost of daring greatly, but each one, without exception, changed everything. That's what this journey is about: the 30 space events that didn't just make headlines but reshaped the world. We're talking about explosions of innovation, political turning points disguised as engineering feats, and quiet breakthroughs that whispered the future into existence. This isn't just a list, it's a time machine. By the end, you'll see the night sky differently, not just as stars and emptiness, but as a living story where humanity took its first shaky steps toward becoming an interstellar species. So buckle up, we're about to revisit the moments that didn't just define space exploration but defined us. It began with a beep, a simple, pulsing radio signal that sent shockwaves across the globe. On October 4, 1957, the Soviet Union launched a polished metal sphere no bigger than a beach ball into orbit. Sputnik 1, the world's first artificial satellite, weighed just 184 pounds, but its impact was immeasurable. For 21 days, it circled Earth every 96 minutes, its 4 antennae transmitting that now iconic chirp. Amateur radio operators as far away as Australia could pick up the signal, a haunting reminder that humanity had crossed a threshold. The space age wasn't coming, it had arrived overnight. What made Sputnik so terrifying to the West wasn't just the technology, it was what it implied. If the Soviets could hurl a satellite into orbit, they could likely launch a nuclear warhead across continents. The Cold War had just escalated into the stratosphere. Newspapers ran panic-stricken headlines. American schoolchildren practiced duck and cover drills beneath their desks. Politicians scrambled to respond, and within months, the United States founded NASA, pouring billions into science, education, and rocket research. But the real genius of Sputnik was its simplicity. The satellite carried no cameras, no advanced instruments, just a battery, a transmitter, and a lesson for the world. Space was no longer the realm of science fiction. Few remember that Sputnik's beeps were actually 2 different frequencies, a deliberate choice so scientists could study how radio waves traveled through the ionosphere. Or that its polished surface wasn't just for show. The mirrored exterior helped regulate temperature in the harsh vacuum of space. Even its orbit was calculated with precision, angled to maximize global coverage so no corner of the Earth could ignore its presence. The Soviets didn't just win a propaganda victory, they rewrote the rules of geopolitics. Overnight, rocket scientists became as valuable as generals, and the classroom became a new battlefield. The space race had begun, not with a roar, but with a steady, rhythmic beep that still echoes through history. Just 23 days after Alan Shepard became the first American in space, the Soviet Union dealt another staggering blow to the West, one that would echo for generations. On April 12, 1961, A 27-year-old fighter pilot named Yuri Gagarin squeezed into a spherical capsule barely larger than a washing machine and was hurled into orbit aboard Vostok 1. For 108 minutes, as his spacecraft circled Earth at 17,000 miles per hour, Gagarin witnessed what no human ever had: sunrise over Africa, the curvature of the planet draped in twilight, and the sheer fragility of our world suspended in endless black. His only transmission during the flight was as poetic as it was simple: "The Earth is blue, how wonderful, it is amazing." But behind this triumph lay a web of Cold War intrigue. Soviet engineers had raced to beat the Americans at all costs, cutting corners that would horrify modern safety standards. Gagarin's capsule lacked thrusters to adjust its orbit. His re-entry involved ejecting at 23,000 feet and parachuting separately from the spacecraft, a fact hidden for years to meet international aviation records. Even the launch sequence was a gamble. The rocket's upper stage had failed in half its test flights. Yet when Gagarin landed in a field near Saratov, smiling at startled farmers, the world saw only flawless victory. Overnight, his boyish grin and humble charm turned him into a global symbol, proof that communism could outperform capitalism in the ultimate technological arena. The political earthquake was immediate. American newspapers splashed headlines like "Reds put man in space." President Kennedy, scrambling to respond, would commit the U.S. to landing on the moon within the decade just 6 weeks later. Meanwhile, Gagarin embarked on a worldwide victory tour, mobbed by crowds from London to Havana. Children named goldfish after him. Factories crank out souvenir busts. His quote, "I see no God up here," likely fabricated by Soviet propagandists, became a rallying cry for atheism. Yet the man himself remained disarmingly human. When Queen Elizabeth II asked how he'd eaten in space, he confessed through a translator, "They had me in a tube like toothpaste." What often gets lost in the grandeur is how profoundly Vostok 1 altered human psychology. For millennia, the stars had been the realm of gods and myths. Now a carpenter's son who'd survived Nazi occupation as a child had floated among them. Gagarin's flight didn't just advance technology, it expanded humanity's imagination of what was possible. Every astronaut since, from Neil Armstrong to the crew of the International Space Station, traces their lineage to that single orbit, a lonely metal ball where, for the first time, a human heartbeat resonated in the cosmos. July 16, 1969, 3 men strapped into a spacecraft no roomier than a minivan perched atop a rocket taller than the Statue of Liberty. The Saturn V's engines ignited with a force equal to 85 Hoover dams, shaking the Florida coast as Apollo 11 clawed its way into history. 4 days later, when Neil Armstrong's boot sank into the lunar dust, it wasn't just a footprint left behind. It was a cultural detonation that rewired humanity's self-image forever. What's often forgotten is how many things had to go perfectly wrong for this moment to happen. The lunar module Eagle overshot its landing site by 4 miles, its computer flashing overload alarms as Armstrong manually steered over a boulder-strewn crater with just 30 seconds of fuel remaining. Back on Earth, a single errant heartbeat in the astronaut's biosensors would have triggered an automatic abort. Even the famous "one small step" almost didn't happen. NASA lawyers insisted Armstrong say "a man" rather than "one" for contractual reasons, a nuance lost in the crackling radio transmission. The geopolitics were just as fraught. With the Vietnam War raging and American cities in turmoil, the moon landing was Kennedy's Cold War endgame played to perfection. The Soviets had already lost the race when their N-1 rocket exploded weeks earlier, a failure so catastrophic Moscow banned all photography of it. Yet Apollo 11's triumph wasn't just about beating the USSR. That handwritten plaque on Eagle's ladder, "We came in peace for all mankind," carried dual meanings. It was an olive branch to the world, yes, but also a flex, Only America could afford to be this generous after spending $25 billion, $200 billion in today's money to get there. Then there were the quiet human details. Buzz Aldrin secretly took communion on the lunar surface with a wine and wafer kit blessed by his pastor. The astronauts left behind medals honoring Soviet cosmonauts who died in training, turning rivalry into tribute. And when Michael Collins orbited alone in the command module, he became the most isolated human in history, unable to see Earth or hear radio signals for 48 minutes each orbit. Technologically, the mission was a house of cards built by geniuses. The spacecraft's computer had less power than a modern calculator. Engineers used slide rules to plot trajectories. Even the flag was a last-minute hack. Its aluminum pole had to fold like a shower curtain rod because no one knew how hard moon dust would be to penetrate. Yet this cobbled-together marvel achieved something our ancestors thought divine. Touching another world, Armstrong's heartbeat, recorded at 156 beats per minute during the landing, tells the real story. This wasn't some sterile government project. It was raw, trembling humanity stretched to its absolute limit, and somehow impossibly succeeding. When he radioed, "The Eagle has landed," it wasn't just a spacecraft touching down. It was the weight of centuries of dreaming finally finding solid ground. From the moment it left Earth's atmosphere, the Hubble Space Telescope was destined to rewrite the textbooks, but not in the way anyone expected. When the shuttle Discovery deployed Hubble in April 1990, scientists eagerly awaited crystal-clear images of distant galaxies. Instead, they got blurry smudges. A flaw in the telescope's primary mirror, polished just 0.002 of a millimeter too flat at the edges, rendered its billion-dollar vision nearly useless. The most expensive scientific instrument in history had become a cosmic embarrassment. Then came one of NASA's greatest saves. Engineers designed corrective lenses, essentially eyeglasses for Hubble, installed during a daring 1993 shuttle repair mission. Astronauts in bulky spacesuits performed 5 grueling days of orbital surgery, swapping out instruments like camera sensors and solar panels with the precision of watchmakers. When the first corrected images streamed back, the universe snapped into focus. Suddenly, we could see stars being born in the Eagle Nebula's pillars of creation, detect supermassive black holes lurking in galactic cores, and witness the aftermath of Comet Shoemaker-Levy 9's Jupiter impact. Hubble didn't just observe space, it turned the cosmos into a living, evolving theater. The telescope's real genius lay in its adaptability. Over 5 servicing missions, astronauts upgraded its instruments like swapping lenses on a camera. Each visit gave Hubble new superpowers: infrared vision to peer through cosmic dust, ultraviolet sensors to trace newborn stars, and wide-field cameras to capture galaxies forming at the dawn of time. Its data settled debates no Earth-bound telescope could resolve, confirming the universe's accelerating expansion, proving the existence of dark energy, and even helping pinpoint the age of the cosmos at 13.8 billion years. But Hubble's cultural impact transcended science. Its images became shared human treasures: the glowing Sombrero Galaxy, the ethereal Butterfly Nebula, the breathtaking ultra-deep field revealing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. These weren't just pretty pictures, they reshaped how humanity sees its place in the universe. School projects, screensavers, and museum exhibits bore witness to a simple truth: we are smaller and yet more connected than we ever imagined. The mirror flaw that nearly doomed Hubble became its defining parable. What began as a humiliating engineering failure transformed into a testament to human ingenuity, not just fixing a mistake, but turning it into something revolutionary. For over 30 years, this orbiting observatory has been our eye on the cosmos, proving that sometimes the clearest vision comes from embracing imperfection and daring to look deeper. The Martian surface was once considered a barren wasteland until a convoy of robotic geologists rolled onto the scene and rewrote the red planet's entire history. When NASA's Spirit and Opportunity touched down in January 2004, they weren't just machines, they were time travelers. Designed for 90-day missions, these golf cart-sized rovers uncovered clues that Mars had once been warm, wet, and possibly habitable. Opportunity alone would outlast its warranty by 57 times, trekking 28 miles across cratered plains before finally succumbing to a global dust storm in 2018. Its last message to Earth, "My battery is low and it's getting dark," wasn't just an engineering alert. It was a eulogy for the little rover that redefined perseverance. What these rovers found was nothing short of revolutionary. Spirit discovered opaline silica deposits near home plate, a clear sign of ancient hot springs. Opportunity stumbled upon hematite, blueberries, tiny mineral spheres formed in acidic water. Then came Curiosity in 2012, a Mini Cooper-sized laboratory that drilled into Martian bedrock and hit the jackpot, organic molecules preserved in 3-billion-year-old mudstone. These weren't just chemicals, they were the building blocks of life, surviving in a shallow lake that once lapped at Gale Crater's shores. Every wheel track told a story of rivers carving valleys, of lakes evaporating into salt pans, of a world that may have whispered to microbial life before turning to dust. The engineering behind these missions was equally groundbreaking. Spirit and Opportunity pioneered airbag landings, bouncing across the surface like interplanetary beach balls before unfolding. Curiosity introduced the jaw-dropping sky crane maneuver, where a rocket-powered hovercraft lowered the rover on cables before safely crashing itself away. Perseverance, landing in Jezero Crater in 2021, took it further, deploying the first interplanetary helicopter, Ingenuity, whose carbon fiber blades spun at 2,500 RPM in Mars thin air to prove powered flight was possible. But the real magic lay in how these machines humanized Mars. Opportunity's selfies showed its dusty solar panels like a workhorse catching its breath. Curiosity's drill holes looked like an archaeologist carefully brushing soil from fossils. Perseverance even carries 19 cameras, turning every rock study into a cinematic vista. These weren't cold, distant instruments, they became our eyes and hands on another world, scouting landing sites for future astronauts and caching samples for eventual return to Earth. The rover's legacy extends beyond science. They've inspired generations of engineers, spawned countless memes from Opportunities, death to Curiosities, dinosaur, rock, and even starred in Twitter threads written in their own voices. More crucially, they've transformed Mars from a reddish dot in the sky into a tangible frontier, one with drinkable ice locked in its soil and caves that could shelter human explorers. When Perseverance's parachute unfurled with a hidden message reading, "Dare mighty things," it wasn't just NASA motto. It was the spirit of every rover that came before, proving that even our smallest emissaries can change how we see ourselves, not just as earthbound creatures, but as neighbors in a solar system ripe for exploration. January 28, 1986 was supposed to be a day of celebration. The Space Shuttle Challenger's mission had captured the nation's imagination, partly because of crew member Krista McAuliffe, a high school teacher chosen from thousands to become the first ordinary citizen in space. Children across America crowded into classrooms to watch the launch live, eager to see history unfold. But 73 seconds after liftoff, a fireball tore across the blue Florida sky, scattering debris into the ocean below. The explosion wasn't just a technical failure, it was a collective wound that scarred a generation's trust in space exploration. The technical culprit was chillingly mundane, a rubber O-ring seal in one of the solid rocket boosters, designed to prevent hot gases from escaping. Overnight, this tiny component became synonymous with catastrophic failure. engineers at Morton Thiokol, the contractor responsible for the boosters, had warned NASA about the O-ring's vulnerability in cold weather. The night before launch, temperatures at Cape Canaveral plunged to 18 degrees Fahrenheit, far below the material's safe threshold. Ice coated the launch pad, and yet, under pressure to maintain an ambitious flight schedule, managers overruled the engineers' concerns. The decision had fatal consequences. As Challenger ascended, the frozen O-ring failed to expand, allowing flames to breach the booster and ignite the external fuel tank. Beyond the engineering failure, Challenger exposed deeper flaws in NASA culture. The agency had begun treating the shuttle as routine, a space truck, rather than the experimental vehicle it truly was. Missions were scheduled back-to-back to justify the program's enormous costs, and safety protocols had grown lax. The disaster forced a reckoning. The Rogers Commission, tasked with investigating the accident, didn't just cite the O-ring, it blasted NASA's broken decision-making process. For 32 months, shuttles remained grounded while the agency overhauled procedures, redesigned components, and created an independent safety office. Krista McAuliffe's presence added a layer of raw humanity to the tragedy. She wasn't an astronaut by profession. She was a social studies teacher from New Hampshire who'd won the Teacher in Space contest with her infectious enthusiasm. Her lessons, planned to be broadcast from orbit, were meant to inspire students to dream bigger. Instead, her death became a sobering reminder of exploration's risks. Schools renamed in her honor, scholarships were established, and the Challenger Center for Space Science Education was founded to continue her mission of inspiring young minds. The disaster's cultural impact rippled far beyond NASA. Late-night comedians stopped joking about space launches. Congress slashed the shuttle program's budget. Public support for human spaceflight plummeted, yet Challenger also sparked something unexpected: a renewed reverence for the astronauts who dared to push boundaries. Their families channeled grief into advocacy, ensuring the crew's legacy wasn't defined by how they died, but by what they stood for: courage, curiosity, and the unshakable belief that progress demands risk. When shuttles finally returned to flight in 1988, the first mission carried a symbolic payload: thousands of handwritten letters from children, proving that even in tragedy, the dream of space endured. Challenger's wreckage, painstakingly recovered from the ocean floor, now rests in a missile silo at Cape Canaveral, a silent memorial and a permanent reminder. The accident didn't just change how rockets were built, it changed how we weigh risk against ambition. Every modern safety protocol, every go/no-go checklist, even SpaceX's culture of transparency traces back to those 73 seconds. The flames that consumed Challenger didn't end the space age. They forged a harder, wiser path forward. For centuries, astronomers assumed planets beyond our solar system were purely theoretical until a Swiss team aimed their telescope at a sun-like star 150 light-years away and found proof the universe was far stranger than we imagined. In October 1995, Mitchell Mayer and Didier Queloz announced the discovery of 51 Pegasi b, a Jupiter-sized world orbiting its star every 4 days. This wasn't just a new planet, it was a cosmic rule-breaker. 51 Pegasi b defied all expectations by clinging absurdly close to its sun, glowing at 2,000 degrees Fahrenheit and completing orbits faster than Mercury. Overnight, the textbook definition of a solar system was obsolete. The detection method itself was revolutionary. Instead of seeing the planet directly, the team measured its gravitational tug on the host star. As 51 Pegasi b whipped around its orbit, the star wobbled like a spinning top with a slight rhythm, just 11 meters per second, a gentle walking pace detectable only by splitting starlight into wavelengths with precision finer than 1 part in 10 million. This radial velocity technique became a blueprint for discovery. Within a decade, hundreds more hot Jupiters were found, many orbiting backward or tilted at bizarre angles. proving our orderly solar system was the exception rather than the rule. Then came NASA's Kepler Space Telescope in 2009, a planet hunting machine that worked like a celestial census taker. For 4 years, Kepler stared unblinking at one patch of the Milky Way, monitoring the brightness of 150,000 stars for the telltale dimming caused by planets crossing their faces. The numbers were staggering, over 2,700 confirmed exoplanets, with thousands more candidates waiting in the data. Kepler revealed that planets outnumber stars in our galaxy, each one a potential home for something or someone looking back at us. Some systems defied logic entirely, like Kepler 16b, a Tatooine-like world orbiting twin suns, or K218b, a watery super-Earth twice our size with a hazy hydrogen atmosphere. But the real treasure hunt was for Earth twins planets in the Goldilocks zone where liquid water could exist. Kepler 452b, discovered in 2015, became the first near-Earth-sized planet orbiting a Sun-like star at the right distance. Then came the TRAPPIST-1 system in 2017, 7 rocky worlds crammed so tightly around a dim red dwarf that standing on one would reveal neighboring planets looming larger than our moon. These discoveries transformed astrobiology from speculation into urgent science. Telescopes like James Webb now analyze exoplanet atmospheres for biosignatures, oxygen, methane, or even industrial pollutants that might hint at distant civilizations. The cultural impact has been equally profound. Science fiction tropes of alien worlds shifted from fantasy to plausible futures. Kids learning about the solar system today grow up knowing it's just one of billions. The search for exoplanets has even birthed citizen science projects like Planet Hunters, where anyone can sift through Kepler data and potentially spot a new world. What began as a single wobbling star has blossomed into a cosmic realization. The universe teems with planets, each a blank slate for nature's creativity. Whether any harbor life remains unknown, but one thing is certain: we've crossed from wondering if other Earths exist to asking which one we'll explore first. Imagine a workplace where sunrise happens every 90 minutes, coffee floats in globules, and your daily commute involves strapping yourself to a treadmill to avoid muscle loss. Welcome to life aboard the International Space Station. This football field-sized outpost, assembled piece by piece since 1998, isn't just humanity's most expensive science project, costing over $150 billion. It's a miracle of geopolitics, an orbiting laboratory where former Cold War rivals now share airlocks and meals, proving that even among earthly tensions, the stars can still unite us. The ISS's construction reads like an intergalactic IKEA manual written by diplomats. Russian Proton rockets hauled up the Zarya control module. American shuttles delivered the Unity connecting node. Canada contributed a robotic arm so precise it could pluck a grape from its stem. Europe and Japan added labs with giant bay windows for Earth observation. Over 40 missions across 13 years, astronauts from 15 nations bolted, wired, and pressurized this patchwork habitat while traveling 17,500 miles per hour. The result, a zero-gravity Noah's Ark of human ingenuity, complete with its own Wi-Fi network and a urine recycling system that turns yesterday's coffee into tomorrow's drinking water. Science here happens in ways impossible on Earth. Protein crystals grow purer in microgravity, revealing structures that help design cancer drugs. Flames burn as cool spheres instead of teardrops, teaching us about combustion. Even the station's exterior acts as a testbed. Materials exposed to years of cosmic radiation guide future Mars mission designs, but the most profound experiments study the astronauts themselves. Scott Kelly's year-long mission revealed how space alters DNA methylation and gut bacteria, while Japan's space mice showed artificial gravity could prevent bone loss. Every sunrise through the Cupola Observatory's 7 windows isn't just a photo op. It's a data point in how living off-world changes us biologically and psychologically. Day-to-day life is equal parts routine and surreal. Astronauts wake up strapped to sleeping bags velcroed to walls, then consult schedules printed on waterproof tablets. Workouts involve resistance machines since dumbbells would just float away. Dinner might be rehydrated borscht or thermostabilized fajitas with tortilla as preferred over bread crumbs clog air filters. Even haircuts require vacuum attachments. Yet within this regimented existence, moments of wonder intrude, like watching the aurora ripple below like neon rivers or catching a SpaceX Dragon capsule arriving with fresh supplies. The ISS's true legacy isn't just what we've learned, but how we learned it. When Russian cosmonauts and American astronauts toasted with juice pouches during the Crimea crisis, or when the crew played the first orbital guitar concert during pandemic lockdowns, the station became something rarer than a sanctuary. Its original 15-year lifespan has been extended 3 times because nobody can bear to abandon this symbol of what's possible when we prioritize curiosity over conflict. As private stations loom and lunar gateways rise, the ISS stands as a testament to an idea: that the blackness of space reflects not just the void, but the best of who we choose to be together. Launched just 16 days apart in the summer of 1977, Voyager 1 and 2 weren't just probes, they were time capsules, interstellar ambassadors, and some of the most resilient machines humanity has ever built. Their original mission was simple: swing by Jupiter and Saturn, snap some photos, and beam back data. But 45 years later, these twin spacecraft have done far more than check off planetary flybys. They've redefined the boundaries of human exploration, venturing farther from Earth than any other object we've created, and they're still whispering back to us across the unimaginable void. The sheer audacity of their engineering still stuns. Built before the digital revolution, the Voyagers run on processors with 70,000 times less memory than a modern smartphone. Their cameras, now dormant to conserve power, captured images on analog Vidicon tubes, the same technology once used in television studios. Yet with these primitive tools, they revealed Jupiter's volcanic moon Io, Saturn's intricate ring structure, and Neptune's supersonic winds. Voyager 2 remains the only probe to visit Uranus and Neptune, worlds so distant they're barely more than fuzzy dots in most telescopes. Each flyby was a masterclass in celestial mechanics, using planetary gravity like a slingshot to fling the probes toward their next target, a technique perfected by a young engineer named Gary Flandreau, who calculated the rare alignment of outer planets that made the Grand Tour possible. Then there's the golden record, a 12-inch gold-plated copper disc carrying humanity's greatest hits. Compiled by a team led by Carl Sagan, it's a sonic mosaic of Bach concertos, Chuck Berry's Johnny B. Good, and the haunting strains of a Navajo night chant. There are greetings in 55 languages, from ancient Akkadian to a child's laughter, and 115 analog images etched into the surface, from a diagram of DNA to a supermarket checkout line. The records even include brainwave patterns of a woman in love, recorded as she pondered what message to send the cosmos. Packed with a stylus and playback instructions in symbolic language, they're less scientific instruments than cosmic messages in bottles, proof that even in the cold equations of rocketry, we couldn't resist sending pieces of our soul. Today, the Voyagers are where the solar system ends and interstellar space begins. In 2012, Voyager 1 crossed the heliopause, the invisible boundary where the sun's magnetic influence wanes and the Milky Way's cosmic rays take over. Its instruments detected the change not visually, but through vibrations, like a submarine sensing pressure shifts in deep water. Each probe still phones home using a 23-watt transmitter, weaker than a refrigerator light bulb, their signals taking over 20 hours to reach Earth's network of radio telescopes. Engineers at NASA, a jet propulsion laboratory, some not yet born when the Voyagers launched, still decode their faint pulses, squeezing data from a trickle of electrons. What makes these missions timeless isn't just their longevity. It's how they've grown beyond their original purpose. The Voyagers were designed to study planets, yet their greatest legacy might be teaching us about the space between them. They've measured the interstellar magnetic field, detected plasma waves unlike anything in our solar system, and proven that the universe is far noisier than we imagined. And long after their plutonium power sources fade projected around 2030, they'll drift silently among the stars, the golden records waiting patiently for any civilization curious enough to listen. Perhaps the most poignant detail is one few notice. Both probes carry small uranium samples. Their decay rate acts as a universal clock, letting any future discoverer calculate exactly when these artifacts were launched. It's a final act of foresight from a species that, for all its flaws, still dreams of reaching across the eons. The Voyagers aren't just machines, they're the farthest flung pieces of human hope, and proof that sometimes the quietest signals carry the loudest messages. February 1, 2003 dawned like any other re-entry day. The Space Shuttle Columbia streaked across the western sky at 18 times the speed of sound, its heat shield glowing cherry red as it sliced through the upper atmosphere. For 16 days, the 7 astronauts aboard had conducted groundbreaking research, studying fire behavior in zero gravity, growing protein crystals for medical research, even observing spider webs spun in space. No one watching the live NASA feed noticed anything amiss until the first flickers of debris appeared over Texas at 8:59 a.m. Within minutes, the impossible became horrifyingly real. Columbia was breaking apart, scattering wreckage across 3 states and taking with it one of NASA's most diverse crews, including Israel's first astronaut and a mother of 2 who'd dreamed of space since childhood. The tragedy traced back to a moment 82 seconds after launch, when a suitcase-sized chunk of insulating foam tore loose from the external fuel tank and slammed into the shuttle's left wing at 530 miles per hour. Mission managers reviewed camera footage showing the impact but dismissed concerns. After all, foam had been shedding since the earliest shuttle flights. What they didn't know was that this strike had punched a dinner plate-sized hole in the reinforced carbon-carbon panels protecting the wing's leading edge. As Columbia re-entered, superheated plasma hotter than the surface of the sun seeped into the breach like a blowtorch, melting aluminum struts and severing hydraulic lines until aerodynamic forces ripped the orbiter apart. Investigators later reconstructed the crew's final moments with chilling detail. The first alarm woke them at 8:54 a.m. as sensors detected rising temperatures in the landing gear wheel well. Within 90 seconds, control was lost, hydraulic pressure gone, aerodynamic drag spiking. The cabin likely lost pressure before structural breakup, sparing them the worst horrors. Yet amid the chaos, recovered data showed pilot Willie McCool and Commander Rick Husband fighting to regain control to the last second, their training overriding any panic. The Columbia Accident Investigation Board unearthed disturbing parallels to Challenger's 17 years earlier complacency layered upon technical failure. NASA had normalized foam shedding as in-family rather than addressing the known issue. Engineers who expressed concern were sidelined by managers fixated on schedule. Most damningly, the board discovered the agency could have potentially mounted a rescue mission using Shuttle Atlantis, already being prepped for launch. The 7 astronauts might have been saved had warnings been heeded. Cultural aftershocks rippled worldwide. Native American tribes performed purification ceremonies where debris fell in Louisiana. A rabbi in Jerusalem eulogized astronaut Ilan Ramon, who'd carried a Torah scroll salvaged from the Holocaust. NASA canceled all shuttle flights for 29 months, overhauling inspection protocols and designing new foam application techniques. But the deepest change was philosophical, the realization that reusable spacecraft weren't inherently safer, just differently vulnerable. When shuttles resumed flying in 2005, each mission carried the unspoken mandate, never again. Columbia's legacy lives in quieter ways in the Day of Remembrance, observed annually at NASA centers. in the trees grown from recovered debris seeds distributed to schools, and most profoundly in the retirement of the shuttle program itself in 2011. The accident didn't just claim lives, it shattered the illusion that space travel could ever become routine. Every modern safety protocol, from SpaceX's redundant parachutes to Boeing's thrice-checked seals, bears the invisible fingerprints of those lost lessons. The final crew never reached their intended runway, but their sacrifice paved a harder, wiser path to the stars. Denis Tito boarded a Russian Soyuz spacecraft in April 2001, knowing he'd make history, not as an astronaut, but as the first private citizen to buy a ticket to space. The 60-year-old millionaire and former NASA engineer had shelled out a reported $20 million for an 8-day stay aboard the International Space Station, a move that outraged NASA administrators but signaled the dawn of a new era. As the Soyuz docked with the ISS, professional astronauts initially gave Tito the cold shoulder, with one NASA official even calling the arrangement a taxi ride that jeopardized serious science. But when Tito floated into the station wearing his custom-made flight suit, pressing his face to the cupola to weep at the sight of Earth, something unexpected happened. The skeptics began to soften. Tito's journey was more than a rich man's joyride. It exposed the brittle politics of space access. NASA had fought tooth and nail to block his flight, citing safety concerns and arguing the ISS wasn't a tourist destination. But Russia's cash-strapped space agency, Roscosmos, saw an opportunity. They'd already sold seats to Japanese and European astronauts under commercial agreements. Why not open the door wider? The resulting tension revealed a fundamental shift. Space was no longer solely the domain of governments. A California financier with no official training had breached the celestial gates, proving that with enough money and determination, the stars could belong to anyone. The ripples from Tito's trip spread quickly. By 2004, Microsoft co-founder Charles Simonyi followed suit, paying $25 million for his orbital vacation. South African tech mogul Mark Shuttleworth brought along science experiments to legitimize his flight, blurring the line between tourist and researcher. But the real revolution came from the companies watching these pioneers. Elon Musk's then fledgling SpaceX saw proof that private spaceflight had a market. Jeff Bezos's Blue Origin began quietly developing New Shepard, a suborbital rocket designed specifically for paying customers. Even Richard Branson's Virgin Galactic pivoted from satellite launches to space tourism after recognizing the public's hunger for a taste of zero gravity. Critics raised valid concerns. Would wealthy tourists divert resources from critical research? Could untrained civilians handle emergencies? The ethical debates grew louder as companies promised lunar hotels and Mars cruises. Astronauts like Chris Hadfield warned that treating space like a theme park risked trivializing its dangers, while astrophysicists fretted over the carbon footprint of rocket joyrides. Yet proponents countered that tourism could democratize space, funding advancements that trickled down to scientific missions. When SpaceX sent the all-civilian Inspiration 4 crew to orbit in 2021 without any professional astronauts aboard, it was clear Tito's gamble had evolved into an industry. Today, the line between tourist and explorer keeps blurring. Axiom Space now sells ISS modules for private use, while SpaceX's Starship promises affordable lunar flybys. The original $20 million price tag seems quaint compared to the $500 million private missions being planned. But Tito's tearful gaze at Earth still lingers as a reminder. Space tourism was never just about escapism. It was about proving that the cosmos isn't a guarded clubhouse, but a frontier waiting for all of humanity to stake its claim. As orbital hotels rise and lunar tickets sell out, that fragile Soyuz flight in 2001 stands as the moment the universe stopped being a destination and started feeling, for better or worse, like home. For nearly a century, gravitational waves existed only as scribbles in Einstein's equations, a mathematical quirk suggesting that cataclysmic events in space should send ripples through the very fabric of spacetime itself. But on September 14, 2015, an instrument shaped like a gigantic L caught something extraordinary. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal so faint it defied belief, a passing wave stretching and squeezing space itself by less than 1,000th the width of a proton. This wasn't just a technical achievement, it was humanity tuning into the universe's hidden soundtrack for the very first time. The source of that signal was a cosmic collision of staggering violence, two black holes, each roughly 30 times the mass of our Sun, spiraling toward each other at half the speed of light. 1,200 million years ago, in a galaxy far beyond our own, they finally merged, releasing a burst of energy equivalent to 3 suns converting entirely into pure gravitational waves. By the time those waves reached Earth, they'd traveled across eons, weakening to a whisper that made LIGO 4-kilometer-long arms wobble by an almost imperceptible amount. The detection required precision beyond imagination. Lasers measuring changes smaller than an atom, vacuum chambers cleaner than interplanetary space, and algorithms capable of filtering out vibrations from passing trucks and distant ocean waves. What made this discovery revolutionary wasn't just confirming Einstein's prediction. It was the birth of an entirely new way to observe the cosmos. Traditional astronomy relies on light, visible, X-ray, radio, but gravitational waves let us hear the universe instead. That first detection revealed details no telescope could capture. The black hole's final orbits, the milliseconds-long chirp as they merged, even the ring down as the new, larger black hole settled into its spherical shape. Suddenly, we could study phenomena invisible to electromagnetic instruments, like collisions in dust-filled regions of space or events from the universe's earliest epochs before light could travel freely. The ripple effects extended far beyond astrophysics. LIGO's success proved that massively ambitious, decades-long experiments could pay off. Its founders had waited 40 years for this moment. It sparked a global race to build even more sensitive detectors, from Japan's Kagra to the planned space-based LISA mission. Most profoundly, it ushered in the era of multi-messenger astronomy, where gravitational waves act as cosmic tripwires alerting telescopes where to look. When LIGO detected 2 neutron stars colliding in 2017, observatories worldwide swiveled to catch the aftermath gamma-ray bursts, glowing kilonovae, even the creation of heavy elements like gold and platinum. Einstein himself doubted we'd ever detect these waves, calling them too weak to measure. Yet here we are, listening to black holes sing across the abyss. Every new detection adds to the symphony, the groaning of neutron stars, the rumbles of supernova, perhaps someday the echoes of the Big Bang itself. LIGO didn't just open a new window on the cosmos, it tore down the wall between us and the universe's most secret conversations, proving that even spacetime itself has stories to tell. Deep in the asteroid belt, a frozen relic the size of a mountain tumbled silently through space until a washing machine-sized spacecraft named Rosetta caught up with it after a 10-year chase. Comet 67P/Churyumov-Gerasimenko, with its bizarre rubber duck shape and crackling jets of gas, became the most studied dirty snowball in history when Rosetta became the first probe to orbit a comet in August 2014. What made this mission extraordinary wasn't just the precision required to match 67P's 33,000 mile-per-hour orbit. It was the audacious plan to send a lander named Philae down to its fractured surface, a maneuver so risky engineers compared it to throwing a dart from London and hitting a bullseye in Sydney while both were moving. Philae's landing quickly veered from textbook to heart-stopper. When its harpoons failed to fire, the 100-kilogram lander bounced off the comet's surface not once but twice before coming to rest sideways in a shadowy crevice. With just 60 hours of battery life left, Philae's scientists raced against the clock, deploying drills to sample 67P's crust while the lander's awkward angle made every experiment a Hail Mary pass. The final transmission before power loss showed sublimating ice crystals glittering like diamond dust under weak sunlight, a haunting farewell from humanity's first cometary outpost. Yet even in failure, Philae delivered gold. Its compromised position accidentally allowed instruments to sniff organic molecules like methyl isocyanate and acetone, chemical building blocks for amino acids that would have been vaporized in sunlight. Meanwhile, Rosetta's 17 scientific instruments mapped 67P in unprecedented detail, discovering towering cliffs of water ice, sinkholes spewing cyanide gas, and a daily weather cycle where the comet's day side cracked like desert mud under solar heat. Most startling was the detection of molecular oxygen in the comet's coma, a gas that shouldn't survive billions of years unless preserved in deep freeze since the solar system's birth. The mission's true revelation lay in 67P's water. Rosetta's mass spectrometers proved its hydrogen isotopes didn't match Earth's oceans, challenging the long-held theory that comets delivered our planet's water. Instead, the data pointed toward asteroids as the primary carriers, a cosmic plot twist rewriting the story of how life gained its most essential ingredient. When Rosetta itself made a controlled crash into 67P in September 2016, its final images showed pits lined with goosebump structures, primordial rubble from the solar system's construction phase, preserved like a 4.6 billion-year-old time capsule. What began as a bumpy landing became a masterclass in adaptation. Philae's struggle mirrored the comet's own chaotic journey, a battered survivor from the solar system's violent youth. Together, Rosetta and Philae didn't just study a comet. They gave us front-row seats to our cosmic origins, proving that even the messiest scientific endeavors can unveil the universe's cleanest truths. The countdown hit zero at 3:45 p.m. Eastern Time on February 6, 2018. And in an instant, the Kennedy Space Center shook with a roar that hadn't been heard since the Apollo era. SpaceX's Falcon Heavy, the most powerful operational rocket in the world, tore through the Florida sky with 3 boosters and 27 engines firing in unison, enough thrust to lift 64 metric tons into orbit. But this wasn't just any payload nestled inside the fairing. Strapped to the rocket's nose cone was Elon Musk's personal cherry red Tesla Roadster, blasting David Bowie's Life on Mars. From its stereo as it embarked on the ultimate joyride, an elliptical orbit around the sun that would take it beyond Mars, the sheer audacity of the stunt captured imaginations worldwide. A spacesuit-clad mannequin nicknamed Starman sat behind the wheel, one hand casually resting on the Tesla's dashboard while the Earth shrank to a blue marble in the rearview mirror. Live cameras mounted on the car streamed the surreal scene back to millions watching online, transforming what could have been a routine test flight into a pop culture phenomenon. Yet beneath the viral spectacle lay serious engineering breakthroughs. The Falcon Heavy wasn't just powerful, it was revolutionary in its reusability. Minutes after launch, 2 of its side boosters returned to Earth in perfect synchrony, landing side by side at Cape Canaveral like something out of a science fiction film. The center core, though it missed its drone ship landing, proved that even the heaviest rockets could now be flown more like airplanes than disposable fireworks. Cost savings became the real headline. Traditional heavy-lift rockets like United Launch Alliance's Delta IV Heavy came with a price tag of $350 million per launch. SpaceX slashed that to $90 million by reusing hardware, a disruption that sent shockwaves through the aerospace industry. Suddenly, NASA could dream bigger with interplanetary probes. Private companies saw a path to deploying massive satellite constellations. Even the Pentagon took notice, shifting contracts toward reusable platforms. The Falcon Heavy's success wasn't just about horsepower. It was proof that innovation could break the cycle of astronomical launch costs that had stifled space exploration for decades. Critics dismissed the Tesla stunt as a billionaire's vanity project, but Musk's gambit had a deeper purpose: By making space fun again, by putting a convertible on a cosmic highway, he shattered the perception that rocket science had to be dull government bureaucracy. Kids who'd never cared about payload capacities now glued themselves to live streams. Memes of Starman flooded social media. The launch rekindled something space agencies had struggled for years to articulate. That exploration isn't just about data points and funding reports. It's about wonder. When the Roadster's final booster burn sent it hurtling toward the asteroid belt, it carried more than just a car. Tucked in its glove compartment was a copy of Isaac Asimov's Foundation series, a nod to humanity's enduring dream of reaching the stars. The Falcon Heavy didn't just prove rockets could be reused, it reminded us why we build them in the first place, not just to calculate trajectories, but to chase the kind of future where even the sky isn't the limit. For centuries, Mars teased us with hints of water-polar ice caps that grew and shrank with the seasons, river valleys carved by ancient floods, even pebbles rounded by what could only be long-lost streams. But in September 2015, NASA dropped a bombshell. Liquid water wasn't just part of the red planet's past. It was flowing right now in our lifetime, in dark streaks that slithered down crater walls like ghostly fingers. These mysterious features, called recurring slope lineae, had been spotted years earlier by the Mars Reconnaissance Orbiter, but their true nature remained debated until spectral analysis revealed hydrated salt's chemical fingerprints left behind as briny water evaporated in the thin Martian air. The discovery was a masterclass in planetary detective work. The orbiter's compact reconnaissance imaging spectrometer for Mars, or CRISM, didn't see the water directly. Instead, it detected perchlorates, salts that lower water's freezing point enough to keep it liquid at -94 degrees Fahrenheit. These weren't raging rivers, but thin films of super salty sludge oozing from underground aquifers or melting ice. The streaks appeared during warmer months, stretching hundreds of feet downhill before vanishing when temperatures dropped, like a seasonal heartbeat pulsing beneath Mars' rusty skin. What made this revelation earth-shaking wasn't just the presence of water. It was the tantalizing possibility of life. Where there's liquid water on Earth, from acidic hot springs to Antarctic brine lakes, there's almost always microbial life clinging to existence. The discovery instantly made Mars recurring slope lineae prime targets for future missions, though with a sobering caveat. NASA planetary protection rules strictly limit how close we can send robots to these areas, lest we contaminate potential ecosystems with earthly bacteria. The Mars Reconnaissance Orbiter had already revolutionized our understanding of the planet, mapping minerals in exquisite detail and scouting landing sites for rovers. But this find cemented its legacy as one of history's most important interplanetary scouts. Its high-resolution camera, HiRISE, captured the streaks at just 12 inches per pixel, sharp enough to distinguish individual boulders in the flow path. Later observations even caught avalanches of dust and ice in action, proving Mars was far from a static desert world. Critics rightfully pointed out challenges. The water's extreme salinity would challenge even hardiest Earth extremophiles, and its fleeting nature made it a harsh habitat. Yet the implications stretched beyond biology. This water could be a resource for future astronauts, convertible to drinking water or rocket fuel. Its very existence hinted at vast underground reservoirs, possibly warmed by geothermal heat. Most profoundly, it transformed Mars in our collective imagination from a dry fossil to a dynamic world with seasons, weather, and maybe, just maybe, neighbors. When the European Space Agency's Mars Express later found evidence of a liquid water lake beneath the South Polar Cap in 2018, it only deepened the mystery. Far from being a dead relic, Mars was whispering secrets about how planets nurture life and where we might find it next. Those faint, temporary streaks became more than geological curiosities. They were signposts pointing toward humanity's next great question. If water flows in our solar system's harshest deserts, how many other oases might we find among the stars? For 9 long years, New Horizons streaked through the silent dark, a washing machine-sized probe carrying the dreams of every kid who ever doodled Pluto at the edge of their solar system map. When it finally reached its target in July 2015, the images that streamed back weren't just photographs. They were love letters from the last unexplored world in our cosmic neighborhood. Pluto, once a blurry smudge in telescopes, unveiled itself as a rugged wonderland of nitrogen glaciers, ice mountains taller than the Rockies, and a heart-shaped basin so pristine it looked painted onto the landscape. This wasn't the dead rock astronomers expected. It was a geologically active time capsule, whispering secrets from the solar system's wild early days. The most jaw-dropping revelation was Tombaugh Regio, that iconic heart-shaped plane stretching 1,000 miles across Pluto's surface. Far from being a static scar, this frozen basin turned out to be a churning conveyor belt of nitrogen ice. New Horizons' infrared scans showed glaciers creeping like slow-motion lava, fueled by Pluto's faint internal heat. Nearby, the jagged peaks of the Norgay Montes revealed water ice as hard as steel, towering 11,000 feet above valleys dusted with reddish-brown tholins, organic molecules cooked up by solar radiation. Most astonishing of all were the snapshots of possible cryovolcanoes, where slushy mixtures of water and ammonia might erupt onto the surface like icy geysers. This tiny world held big surprises about planetary evolution. Pluto's thin atmosphere, first detected during a stellar occultation in 1988, turned out to be layered with blue haze and drifting ice particles. Its moons, especially the chaotic tumbler Charon, bore scars of violent impacts that could rewrite theories of how satellite systems form. And when New Horizons later buzzed the Kuiper Belt object Arakoth in 2019, its snowman-like shape confirmed that these distant relics preserved the original building blocks of planets, untouched for 4.5 billion years. The mission didn't just redefine Pluto, it shattered the old planet vs. dwarf planet debate. How could astronomers dismiss a world with shifting glaciers, weather systems, and possibly even underground oceans? New Horizons principal investigator Alan Stern coined the term explored worlds to emphasize that geology, not size, determines a body's complexity. Suddenly, the Kuiper Belt wasn't just a junkyard of leftovers. It was a frontier teeming with dynamic mini-worlds, each a puzzle piece in understanding how our solar system grew up. What makes New Horizons' triumph linger isn't just the science. It's the human story woven through its trajectory, from the school kids who sent their names on the probe's commemorative CD to the ashes of Pluto's discoverer Clyde Tombaugh riding aboard as silent witness. When the spacecraft turned its camera backward for one last shot, capturing Pluto backlit by the sun in a breathtaking halo of blue haze, it wasn't just saying goodbye. It was proving that even the furthest, loneliest outposts of our solar family have stories worth crossing 4 billion miles to hear. The crackling transmission came 56 hours into the mission, just as Apollo 13's crew finished a live TV broadcast no network bothered to air. "We've had a problem," barely registered on Earth before the spacecraft shuddered with a bang that shook the coffee from Capcom Jack Lausma's cup in Houston. What began as routine oxygen tank stirring erupted into catastrophe when faulty wiring sparked an explosion, blowing the side-off service module Bay 4 and crippling Odyssey, the command module. Commander Jim Lovell's quick glance out the window confirmed their worst fear: oxygen venting into space like glittering snow, the lifeblood of both breathing and power bleeding away. In that heartbeat, Apollo 13 transformed from a lunar landing mission into the most desperate rescue operation in NASA history. Every contingency plan disintegrated along with the oxygen tank. With fuel cells dead, astronauts crammed into the lunar module Aquarius, a lifeboat designed for 2, now sheltering 3. Carbon dioxide scrubbers meant for 45 hours strained under a 90-hour burden. forcing engineers to improvise filters from plastic bags, duct tape, and spare parts in a frantic all-night hack now legendary as the mailbox. Meanwhile, navigators recalculated trajectories using Earth's horizon as a guide when power shortages killed the guidance computer. The cold became unbearable as temperatures plummeted to 38 degrees. Condensation dripped from walls, threatening to short-circuit every switch. What saved them wasn't heroics but meticulous training and collective genius. Engineers at Mission Control repurposed lunar module engines for course corrections despite never testing the maneuver. Astronauts executed a critical 35-second engine burn with no computer, steering manually by keeping a crescent Earth perfectly framed in Aquarius's tiny window. Even the jury-rigged solution for scrubbing CO2 relied on a high school physics lesson, fitting square lithium hydroxide canisters into round holes by forcing air through with a soot hose. The legacy of Apollo 13 echoes in every modern spacecraft design. Redundant systems tripled after the oxygen tank failure exposed single-point vulnerabilities. Future crews trained explicitly in lifeboat scenarios, while mission rules now mandate abort options at every phase. Most profoundly, the near-disaster proved spaceflight's true test isn't reaching destinations but bringing explorers home. A lesson carved into NASA, a culture when Lovell, Hayes, and Swigert splashed down safely despite odds worse than Russian roulette. Their crippled ship still orbits the sun today, a ghostly reminder that in space, survival isn't guaranteed. It's earned through ingenuity, teamwork, and the refusal to accept any outcome but success. For decades, black holes existed as mathematical ghosts predicted by Einstein's equations but forever out of sight, their gravitational grip so strong not even light could escape. Then, on April 10, 2019, the universe's ultimate vault cracked open. The Event Horizon Telescope collaboration unveiled the unimaginable, a photograph of supermassive black hole M87's shadow, 6.5 billion times heavier than our Sun, its dark heart wreathed in a swirling golden halo 55 million light-years away. The image, instantly iconic as a blurry donut, was anything but simple. It represented the work of over 200 scientists across 20 countries, petabytes of data painstakingly assembled like a cosmic jigsaw puzzle. The technical wizardry behind this feat boggles the mind. The HT isn't one telescope but a synchronized network of 8 observatories spanning from Hawaiian volcanoes to Spanish highlands and even the South Pole. By combining their signals through interferometry, a technique that effectively creates an Earth-sized virtual dish, the array achieved resolution fine enough to spot a donut on the Moon. Each station recorded raw data onto helium-cooled hard drives so precise they could measure time down to a trillionth of a second. These drives were then physically flown to central processing centers, since the Internet lacks the bandwidth to transfer such colossal datasets. The final image emerged from half a decade of supercomputer analysis, where algorithms filtered out noise like atmospheric interference and even the rotation of our own galaxy. Why does M87's black hole look like a glowing ring with a dark center? The answer lies in the violent physics at play. The golden halo isn't the black hole itself. It's superheated plasma swirling at near light speed, its light warped into a perfect circle by the black hole's monstrous gravity. The central shadow, roughly 2.5 times larger than the event horizon, marks the point where all trajectories lead inward. Even this seemingly fuzzy snapshot holds treasure troves of data. The brightness asymmetry confirmed Einstein's prediction that material orbiting a black hole would appear brighter on the side, moving toward us, a relativistic effect called Doppler beaming. The ring's thickness hinted at the black hole's spin orientation, while its diameter let scientists double-check M87's colossal mass. Beyond proving black holes aren't just theoretical, the image settled cosmic debates. Some alternative gravity theories had proposed naked singularities without event horizons. M87's shadow proved the horizon exists. The near-perfect circularity confirmed that black holes truly are the simplest objects in the universe, defined by just mass, spin, and charge, as physicist John Archibald Wheeler quipped. Yet mysteries remain. The unexpectedly sharp ring edge suggests plasma might be magnetically confined, like dough squeezed through a cosmic pastry tube. And the faint jet visible in radio observations, a particle beam stretching 5,000 light-years, reminds us this monster is anything but dormant. For all its technical grandeur, the EHT's greatest gift might be philosophical. That glowing ring frozen in the image is actually the combined light from centuries of stellar material, some photons circling for decades before escaping toward our telescopes. We're not just seeing a black hole, we're witnessing a timeline where past and present blur as surely as space-time at the event horizon. The fact that humans could coordinate atomic clocks across continents to capture this proves something profound. Even in an era of division, curiosity remains our universal language. And that fuzzy donut, it's now a beacon, reminding us that the universe's most terrifying wonders are finally, gloriously within view. After 7 years threading its way through the solar system, the Cassini spacecraft arrived at Saturn in July 2004, but it wasn't just there to snap postcards. This nuclear-powered explorer carried the Huygens probe, a European-built lander destined for Titan, Saturn's enigmatic moon shrouded in thick orange haze. What followed wasn't just a mission. It was a 13-year odyssey that peeled back layers of mystery on a planetary system so strange it seemed ripped from science fiction. Cassini didn't just study Saturn, it revealed a miniature solar system teeming with worlds stranger than anything we'd dreamed. First came Titan, where Huygens made history in January 2005 as the first human-made object to land on a moon beyond Earth's orbit. Descending through nitrogen-rich smog thicker than pea soup, the probe's cameras captured river channels cutting through dunes of hydrocarbon sand landscapes shaped not by water, but by liquid methane raining from an alien sky. Huygens' microphone even recorded wind rushing past as it touched down on a damp shoreline, its parachute leaving drag marks in organic sludge. The data painted a chillingly familiar yet utterly alien world. Titan had weather, geology, and chemistry mirroring Earth's, just with methane replacing water at every turn. Meanwhile, Cassini's discoveries piled up like gifts from a cosmic piñata. At tiny Enceladus, geysers of saltwater erupted from a subsurface ocean through cracks in its icy shell, jets so powerful they created one of Saturn's outer rings. Flying just 30 miles above its surface, Cassini tasted these plumes and found hydrogen, a potential energy source for microbial life. Then there was Saturn itself, where a hexagonal storm large enough to swallow 4 Earths raged at the North Pole, a 6-sided vortex spinning in perfect symmetry for decades, defying every fluid dynamics model. Even the rings held surprises: vertical peaks taller than the Rockies, moonlets carving propeller-shaped gaps, and a rain of ice particles falling into Saturn's atmosphere at 10,000 pounds per second. The mission's grand finale was a death dive designed to squeeze every last drop of science from the aging spacecraft. Between April and September 2017, Cassini looped between Saturn and its innermost rings 22 times, a kamikaze ballet that mapped the planet's gravity and magnetic fields with unprecedented precision. When it finally plunged into Saturn's atmosphere, its dying radio signal carried data on atmospheric composition until the very last second, its molecules vaporizing into the planet it had spent a lifetime studying. Cassini-Huygens didn't just expand our knowledge, it rewrote the playbook for what moons could be. Enceladus and Titan joined Europa as top candidates for extraterrestrial life, proving that habitable conditions don't require orbiting a star's Goldilocks zone. The mission's legacy lingers in proposals to send drones to Titan's methane lakes and submarines to Enceladus' hidden sea. More than anything, Cassini taught us that even familiar places like Saturn, a fixture in our night sky for millennia, can harbor wonders beyond our wildest imaginings when we dare to look closer. For over 2 decades, the International Space Station has stood as humanity's sole outpost in orbit, a symbol of global cooperation and scientific endeavor. But now, the celestial neighborhood is getting crowded. As the ISS nears retirement in the 2030s, a new wave of commercial stations is rising to take its place, led by pioneers like Axiom Space with ambitions far beyond government-funded labs. These aren't just replacements, they're reinventions of what life and work in space can be. Picture luxury research pods with panoramic views, factories producing exotic materials in microgravity, even hotels where tourists sip cocktails while floating past Earth's curvature. The era of privatized low Earth orbit isn't coming. It's already being bolted together module by module. Axiom's strategy is as bold as it is pragmatic. Rather than waiting for the ISS to deorbit, they're building their station to dock directly with it initially, like a teenager adding a high-tech room onto their parents' aging house. Their first module, launching as early as 2026, will feature sleek interiors designed by Philippe Starck's studio, with large windows for Earth observation and research bays optimized for pharmaceutical experiments. Unlike the ISS's cramped quarters, every inch is engineered for efficiency and comfort, from ergonomic handrails to noise-dampened sleep pods. But the real game changer is flexibility. Axiom Station can reconfigure on demand, swapping labs for living quarters as client needs shift. One month it might host cancer researchers growing crystalline proteins, the next filmmakers shooting zero-gravity action sequences. The economics behind this shift reveal why private stations are inevitable. Operating the ISS costs NASA over $4 billion annually, a staggering sum when companies like Axiom estimate their stations will slash that figure by 70% through modular design and automated systems. Beyond cost savings, these ventures unlock revenue streams the ISS could never tap. Semiconductor firms paying premium rates to manufacture flawless silicon wafers in vacuum, athletes training in low gravity to reduce joint stress, even artists leasing studios to create works impossible under Earth's pull. Elon Musk famously compared building rockets to maintaining a fleet of commercial airliners. Now that same logic applies to real estate in orbit, yet challenges loom like orbital debris. Without NASA's rigorous safety oversight, critics worry corners might be cut in the race for profitability. A single micrometeoroid strike or software glitch could turn investor enthusiasm into cold feet overnight. And the specter of space gentrification raises ethical questions. Will access be limited to billionaires and corporations, or will mechanisms exist to ensure scientists and developing nations aren't priced out? Companies like Axiom insist their model democratizes access by making spaceflight cheaper overall, but the proof will lie in who actually signs the leases. What makes this transition historic isn't just the technology. It's the philosophical shift from space as a government-backed commons to a marketplace of ideas and industries. The ISS taught us how to live in orbit. Private stations will teach us how to thrive there. When the first commercial crew floats through an Axiom airlock, they won't just be entering a new module, they'll be crossing into an era where low Earth orbit isn't a destination but a foundation. The age of the International Space Station is ending. The age of space as an ecosystem is just beginning. After decades of delays, budget overruns, and heart-stopping technical hurdles, the James Webb Space Telescope finally tore through the Guyana skies on Christmas morning 2021, a shimmering origami of gold and silver tucked inside an Ariane 5 rocket. What unfurled over the next month wasn't just a telescope deployment, it was the most complex cosmic origami act ever attempted. JWST had to execute 344 single-point failure steps perfectly, unfolding a sunshield the size of a tennis court, aligning 18 hexagonal mirror segments to within 1/10,000th of an inch, and cooling its instruments to -387 degrees Fahrenheit, all while hurtling toward a gravitational parking spot 1 million miles from Earth. One misstep and $20 billion of humanity's most ambitious eye on the cosmos could have become floating scrap metal. The tension peaked during the sunshield deployment. 5 hair-thin layers of Captain Plastic, each as large as a singles tennis court, had to unfurl without snagging. Engineers had nicknamed it the Terror, and for good reason. During ground tests, fasteners snapped, sheets tore, and wrinkles formed that could have cooked the telescope with solar heat. Yet in space, the layers peeled apart flawlessly, creating a frigid shadow colder than the dark side of Pluto. This wasn't just engineering, it was wizardry, enabling JWST infrared vision to peer through cosmic dust clouds like an X-ray machine scanning the universe's bones. When the first full-color images dropped in July 2022, they were worth the wait. The Carina Nebula became a psychedelic landscape of newborn stars punching through gaseous cliffs, a stellar nursery where Earth-sized knots of gas collapsed into suns. Stefan's quintet revealed 5 galaxies locked in a gravitational dance, their arms twisted like taffy from collisions. But the real showstopper was JWST Deep Field, capturing galaxies born just 200 million years after the Big Bang, so ancient their light is stretched into infrared wavelengths invisible to Hubble. These weren't just pretty pictures, they were postcards from the cosmic dawn, revealing infant galaxies smaller than the Milky Way's central bulge already buzzing with star formation. Webb's scientific superpowers lie in its infrared eyes. Where Hubble saw the universe's visible light surface, JWST peers into the hidden layers beneath. Its near-infrared spectrograph can sniff the atmospheres of exoplanets for water vapor or methane chemical fingerprints of potential life. Its mid-infrared instrument detects the warm glow of planetary building blocks swirling around young stars, showing us solar systems under construction. Even its fine guidance sensor, originally just for pointing, turned out to be so precise it can spot Jupiter's moons eclipsing the planet from 1,000 light-years away. Critics initially balked at JWST price tag, but its discoveries are already reshaping textbooks. The telescope spotted 6 massive galaxies in the early universe that shouldn't exist under current formation theories, cosmic teenagers, in an era when only infants were predicted. It found water vapor swirling around a rocky exoplanet, hinting at oceans where none were thought possible. And its observations of Uranus revealed atmospheric phenomena so dynamic they made the ice giant look like a target for future probes. What makes JWST revolutionary isn't just its hardware, it's the questions it forces us to ask. Are we alone? How did the first galaxies ignite? What strange chemistry occurs in interstellar clouds? Every photon hitting its golden mirrors carries clues, and with a 20-year lifespan, this telescope is just warming up. After 30 years of development, Webb isn't just Hubble's successor, it's humanity's time machine, dialing the cosmos back to its earliest chapters and daring us to read between the lines. The clock struck 12 on December 11, 2017, and with the stroke of a pen, humanity's lunar dreams reignited. NASA Artemis program, named after Apollo's twin sister in Greek mythology, wasn't just about planting flags this time. It promised something bolder: boots on the moon by 2025, followed by the first woman and person of color, all while building the infrastructure for permanence. This wasn't a rehash of the 60s, it was a cosmic blueprint for turning our celestial neighbor into a stepping stone toward Mars. The audacity lay in the details: a space launch system rocket taller than the Statue of Liberty, a lunar orbiting gateway station straight out of sci-fi, and rovers designed to harvest water ice from permanently shadowed craters, the same resource that could one day fuel rockets bound for the Red Planet. At Artemis' heart throbs the Space Launch System, or SLS, a colossus of aluminum and ambition. Its orange core stage, packed with 735,000 gallons of supercooled hydrogen and oxygen, generates 8.8 million pounds of thrust at liftoff, making it 15% more powerful than Saturn V. But unlike its disposable ancestors, SLS is designed for evolution. The Block 1 variant that launched Artemis 1 in 2022 could carry 27 metric tons to lunar orbit. Future iterations, like the Block 2 cargo configuration, will haul 46 tons, enough to deliver gateway modules or prefabricated moon-base segments. Critics harp on its $35 billion development cost, yet supporters counter that SLS provides something no commercial rocket can: guaranteed heavy lift capability, purpose-built for deep space, with safety margins honed over decades of shuttle-era lessons. Orbiting 250,000 miles from Earth, the Lunar Gateway reshapes how we approach exploration. This donut-shaped outpost, no larger than a studio apartment initially, will serve as a transfer point for astronauts descending to the surface via the human landing system. Solar electric propulsion keeps it maneuverable, while the Halo module's docking ports accommodate everything from Orion capsules to robotic supply ships. Gateway's real genius lies in its location, a near-rectilinear halo orbit that balances lunar access with uninterrupted Earth communications. Scientists salivate over its potential as a zero-gravity lab for studying cosmic radiation's effects on living tissue, a critical hurdle for Mars missions. And when artists' renderings depict its eventual expansion with habitation modules and airlocks, it's hard not to envision a 21st-century version of the Transcontinental Railroad's way stations, pit stops on the path to deeper space. Sustainability separates Artemis from Apollo's sprint. The program's unspoken mantra, "this time to stay," hinges on exploiting lunar resources. Ice deposits at the South Pole's Shackleton crater could be split into hydrogen for fuel and oxygen for breathing. 3D printers might fuse moon dust into radiation shielding. Even the astronauts' approach is different. Whereas Apollo crews trained as pilots, Artemis teams include geologists and engineers skilled in fieldwork, ready to conduct months-long surveys rather than hours-long strolls. Private companies like SpaceX and Blue Origin add another layer, competing to provide lunar landers and supply runs under NASA, a commercial lunar payload services program, a public-private model that slashes costs while accelerating innovation. Yet Artemis faces storms beyond technical hurdles. Congressional funding seesaws with political wins, while international partners like ESA and JAXA juggle their own budgetary constraints. The 2025 timeline seems increasingly optimistic amid SLS delays and spacesuit redesigns. Skeptics ask why we're racing back to the moon when climate change and pandemics demand Earthbound attention. Advocates counter that Artemis spin-offs from advanced water purification to low-gravity medical breakthroughs always find terrestrial applications. More profoundly, they argue that humanity thrives when aiming beyond the horizon. What makes Artemis resonate isn't just rockets or timelines. It's the quiet revolution in how we view the moon, not as a finish line but as a workshop. A place to master deep space living, a proving ground for technologies that might one day dot the Martian plains, and perhaps most importantly, a shared project where nations and corporations collaborate rather than compete, writing the next chapter not in the language of Cold War rivalry but of collective curiosity. The lunar dust awaiting those first Artemis footprints hasn't settled since Apollo. When it does, it'll mark more than a return. It'll signal the moment we stopped visiting the cosmos and started moving in. On September 15, 2021, a Dragon capsule named Resilience streaked into orbit with a crew unlike any before them. 4 ordinary people with no government affiliation, no military flight experience, and a mission that had nothing to do with national prestige. Inspiration 4 wasn't just the world's first all-civilian spaceflight. It was a radical reinvention of who gets to touch the stars, funded by billionaire entrepreneur Jared Isaacman as both a personal dream and a $200 million fundraiser for St. Jude Children's Research Hospital. This 3-day orbital journey proved space wasn't just for career astronauts anymore. The crew composition alone signaled a new era. Isokman, an accomplished pilot but private citizen, handpicked 3 companions representing pillars of the mission's ethos. Haley Arsenault, a 29-year-old physician assistant and childhood bone cancer survivor, became the first person with a prosthetic body part in space, her titanium femur standing as proof that physical limitations needn't ground cosmic ambitions. Chris Sembrowski, a data engineer and Air Force veteran, won his seat through a public donation lottery that raised $13 million for St. Jude. And Cyan Proctor, a community college geosciences professor, earned her spot as the first black female spacecraft pilot through an entrepreneurial competition promoting diversity in STEM. Together, they weren't just passengers, they were living emblems of accessibility, their backgrounds shattering the sterile archetype of the square-jawed astronaut. Training compressed years of NASA preparation into 6 months, focusing on emergencies rather than scientific operations. The crew practiced escaping a spinning Orion capsule in water survival suits, simulated fiery launch aborts in centrifuges, and even camped overnight in SpaceX's Hawthorne headquarters to bond as a team. Unlike professional astronauts who train for specific technical roles, Inspiration 4 team learned broadly. Proctor mastering docking procedures despite her seat having no controls, Arsenault conducting medical experiments on herself to study radiation effects. SpaceX modified the Dragon capsule, replacing the usual docking port with a massive observation dome they nicknamed the Cupola, offering the first all-glass 360-degree view of Earth from orbit, a luxury even ISS astronauts rarely enjoy. Beyond the spectacle, the mission quietly revolutionized space medicine. Biomedical sensors tracked how novice bodies adapted to microgravity, revealing surprising findings like Sembrowski's unexpected resistance to space adaptation sickness. The crew conducted ultrasounds on each other to monitor fluid shifts, while Arsenault's prosthetic provided data on how implants react to cosmic radiation, an overlooked area of study crucial for future civilian travelers. Their donated biological samples joined St. Jude's research database, potentially unlocking insights into childhood cancer treatments. Critics dismissed Inspiration 4 as a billionaire's vanity project, but its legacy still echoes. The mission's live-streamed concerts and casual TikTok updates from orbit, complete with ukulele performances, demystified space travel for millions. When the capsule splashed down off Florida's coast, it didn't just mark the end of a joyride. It proved orbital flight could be inclusive, philanthropic, and even fun. Today, as private missions multiply, from Axiom's ISS visits to Polaris Dawn's planned spacewalks, Inspiration 4 stands as the moment the cosmos stopped feeling like a government preserve and started feeling, for better or worse, like something anyone might reach for. The crew's motto, "Train like an astronaut, think like a civilian," now guides a new generation of starfarers who measure their right to fly not in NASA badges, but in courage, creativity, and the audacity to believe the final frontier has room for us all. In the quiet hum of a radio telescope in West Virginia, a graduate student named Duncan Lorimer was sifting through old pulsar data in 2007 when he spotted something impossible, a 5-millisecond blast of radio waves so powerful it packed more energy than the sun emits in a month. At first, he assumed it was a glitch, but this anomaly, later dubbed the Lorimer burst, turned out to be the first clue to one of astrophysics' greatest modern mysteries, fast radio bursts, or FRB. These cosmic firecrackers flicker across the universe in the blink of an eye, some unleashing as much energy as 500 million suns before vanishing without a trace. Their origins still anyone's guess. The hunt for FRBs quickly became a global obsession, revealing just how little we understand about the universe's most extreme environments. Telescopes from Australia's Parkes Observatory to Canada's CHIME array started catching them, sometimes as isolated events, other times in repeating patterns that ruled out one-time cataclysms like colliding neutron stars. One particularly cheeky repeater, FRB 1211, flared up like clockwork every 16 days for years, taunting theorists with its precision. But the real shock came when scientists traced some bursts back to their home galaxies. Unlike gamma-ray bursts, which tend to erupt from chaotic star-forming regions, FRBs have been spotted everywhere, from serene spiral arms to the outskirts of ancient elliptical galaxies. Whatever's producing them doesn't play by the usual cosmic rules. Magnetar's highly magnetized zombie stars emerged as the leading suspects. These city-sized remnants of supernova have magnetic fields so intense they warp the very fabric of space-time around them. In 2020, astronomers got their best evidence yet when a magnetar in our own galaxy, SGR 1935 plus 21.5, belched out an FRB-like pulse during a violent starquake. But not all bursts fit this mold. Some repeaters spit out waves with polarization patterns suggesting they've twisted through fields stronger than any known magnetar could produce, hinting at even more exotic physics cosmic strings. Primordial black holes, or something we haven't even imagined. The real magic of FRBs lies in what they carry with them. As these waves traverse the cosmos, they interact with the sparse electrons floating between galaxies, slowing down slightly in a way that reveals the universe's hidden scaffolding. By measuring this delay, called dispersion, scientists can map the missing matter that makes up 85% of the universe's atoms but is too diffused to see. It's like using lightning to measure fog. Already, FRBs have helped pinpoint vast halos of gas around galaxies that theories predicted but telescopes couldn't find. What began as a blip in old data has blossomed into an entire field of astronomy, with telescopes now catching dozens of bursts per month. Some researchers dream of using FRBs as universal yardsticks to measure cosmic expansion with unprecedented precision. Others see them as potential alien beacons, though the lack of repeating patterns in most makes deliberate signaling unlikely. But perhaps their greatest gift is humility. In a universe where unknown objects can fling out more energy in milliseconds than our sun does in decades, every solved mystery reveals 10 new questions waiting just beyond the static. Fast radio bursts don't just challenge our models, they remind us that the cosmos still holds cards it hasn't shown us yet. The night sky has guided humanity for millennia, its constellations etched into our myths, its rhythms shaping our calendars. But in May 2019, that ancient vista began to change dramatically as SpaceX launched the first 60 satellites of Starlink, the vanguard of a planned 12,000-strong mega-constellation promising high-speed internet for every corner of the globe. Within hours, astronomers watched in horror as the train of bright dots outshone most stars, their pristine observations suddenly streaked with glowing lines. What began as a solution for rural connectivity had ignited a firestorm over who owns the heavens, and whether progress in one arena could erase centuries of cosmic wonder in another. Starlink's engineering brilliance is undeniable. Each refrigerator-sized satellite uses ion thrusters to maintain precise orbits, while phased array antennas create targeted internet beams far faster than traditional geostationary satellites. By operating in low Earth orbit at around 340 miles up, latency drops from 600 milliseconds to under 40, making video calls and online gaming possible even in remote Alaskan villages or African deserts. The potential societal impact is staggering. 70% of schools in developing nations lack reliable internet, while disaster responders often lose critical comms when terrestrial systems fail. During Ukraine's invasion, Starlink terminals became lifelines, restoring everything from battlefield coordination to hospital communications within hours of deployment. Yet the trade-offs crystallize under a telescope's lens. Professional observatories reported up to 30% of their long-exposure shots ruined by satellite trails, particularly during twilight when sunlight reflects off the spacecraft's solar panels. The Vera Rubin Observatory, designed to scan the entire sky every 3 nights for asteroid threats and cosmic anomalies, estimates Starlink could render 20% of its images unusable. While SpaceX responded by testing darkened visor-sat coatings and sunshades, the fixes only reduce brightness by about 50%, still too bright for sensitive instruments. The deeper concern lies in radio astronomy. Starlink's transmission frequencies overlap with those used to study interstellar molecules, potentially drowning out whispers from the early universe in a static hiss of broadband. The space debris problem adds another layer of unease, with over 4,000 Starlink satellites already aloft, and competitors like Amazon's Project Kuiper preparing their own fleets. Low Earth orbit is becoming a celestial traffic jam. Each new satellite increases collision risks, which could trigger a catastrophic chain reaction known as Kessler syndrome, where cascading debris renders entire orbital altitudes unusable for generations. SpaceX highlights its satellites' autonomous collision avoidance systems and plans for end-of-life deorbiting, but skeptics note that even a 99% success rate would leave hundreds of derelict satellites drifting dangerously. What makes this debate so thorny is the lack of clear legal frameworks. The Outer Space Treaty of 1967 prohibits national sovereignty over celestial bodies but says nothing about corporations littering the commons. Astronomers have proposed orbital dark sky preserves akin to protected lands on Earth, while companies counter that connectivity is a basic human right. The FCC's approval of Starlink hinged on outdated orbital congestion models from the 1990s, highlighting how regulation lags behind innovation. Perhaps the most poignant irony is that Starlink satellites designed to bridge divides have exposed a cultural rift in how we value the sky. For subsistence farmers gaining online market access, their liberation. For indigenous communities who have navigated by stars for centuries, their desecration. The challenge ahead isn't choosing between progress and preservation, but inventing a future where broadband and the Big Dipper can coexist. As constellations, both ancient and artificial, share the same darkness, we're learning the hard way that even the sky has limits, and that our brightest ideas sometimes cast the longest shadows. For centuries, exoplanets existed only as mathematical probabilities, tiny gravitational tugs on distant stars or fleeting shadows crossing their faces. Then, in July 2020, the Very Large Telescope in Chile's Atacama Desert tore down that abstraction with a single snapshot. There, glowing against the Inkai void like fireflies near a street lamp, were two worlds orbiting the young sun like star tubes 8998761. This wasn't an artist's impression or a graph of wobbling starlight. It was the first ever direct image of a multi-planet system around a sun-like star, a cosmic family portrait 800 light-years in the making. What made this image revolutionary wasn't just its beauty, but the near-impossible challenge of capturing it. Planets are ridiculously faint compared to their host stars. TYC's worlds are 10,000 times dimmer than their sun, and traditional telescopes drown them in glare. The VLT overcame this with a coronagraph, a disk that physically blocks starlight like a photographer shielding their lens from the sun, but even that wasn't enough. Adaptive optics mirrors that flex 1,000 times per second to undo atmospheric blurring, sharpen the view, while years of exposure time allowed the team to distinguish the planet's slow orbital motion from background noise. The result, two Jupiter-sized giants, their orbits wider than Pluto's, caught mid-waltz around a star barely 17 million years old, a stellar toddler compared to our middle-aged sun. The implications ripple far beyond one pretty picture. Direct imaging lets scientists analyze exoplanet atmospheres in ways other methods can't. Spectroscopy of these worlds revealed traces of water vapor and complex organic molecules, chemical fingerprints hinting at how gas giants form. Their wide orbits also challenge migration theories. Conventional wisdom said massive planets should spiral inward, yet here they linger in the deep freeze of their outer system. Most tantalizing is what this technique could soon reveal: smaller, Earth-like worlds. Future telescopes like the extremely large telescope, with mirrors nearly the size of soccer fields, might directly image rocky planets in habitable zones, scanning their atmospheres for oxygen or methane. Yet Yuri's portrait also carries a humbling reminder. Those two dots represent a system frozen in adolescence, a glimpse of what our solar system might have looked like before planets settled into their current orbits. When we stare at them, we're not just seeing alien worlds, we're peering into our own cosmic childhood, a time when Jupiter might still have been carving paths through a dusty protoplanetary disk. The image bridges past and future proof of how far we've come in mapping exoplanets, and a preview of the even sharper snapshots waiting just over the horizon. Dust devils swirled across Jezero crater's rusty plains as a tiny helicopter named Ingenuity prepared to make history. On April 19, 2021, this 4-pound rotorcraft, no larger than a tissue box with legs, spun its carbon fiber blades to 2,500 revolutions per minute and lifted off Mars' surface in a whirl of red dust. For 39 glorious seconds, humanity's first aircraft on another planet hovered 10 feet above the ground, snapped a black and white photo of its own shadow, then gently touched down. What sounds like a simple test flight was actually an engineering miracle, a Wright brothers moment played out on a world with air so thin, flying required rewriting the rules of aerodynamics. Ingenuity's very existence was a gamble. Mars' atmosphere is just 1% as dense as Earth's, making lift almost impossible. To compensate, its twin rotors, each 4 feet wide, had to spin 5 times faster than any helicopter on Earth, while lithium-ion batteries kept it aloft despite nighttime temperatures plunging to -90 degrees Fahrenheit. Even basic navigation demanded innovation. With no GPS satellites orbiting Mars, Ingenuity used a solar-powered inertial measurement unit tracking hundreds of movements per second, paired with a downward-facing camera that compared terrain features to preloaded maps. Every flight was a high-wire act. If the helicopter tipped more than 20 degrees, it would tumble irretrievably. What started as a technology demonstration blossomed into a full-blown exploration revolution. Originally planned for 5 test flights, Ingenuity surpassed all expectations, completing over 70 sorties across 3 Earth years. It scouted ahead for its mothership Perseverance, mapping safe routes through boulder fields and identifying intriguing rock formations for closer study. During Flight 12, the helicopter captured breathtaking images of raised ridges, a winding geologic feature that may have formed in ancient flowing water, from angles impossible for ground-based rovers. Later flights pushed boundaries further, climbing to altitudes of 40 feet and covering distances longer than 2 football fields. The implications ripple far beyond Mars. Ingenuity proved that aerial scouts can transform planetary exploration, mapping lava tubes on the Moon or darting between the geysers of Saturn's moon Enceladus. Its stripped-down design, no heavy scientific instruments, just cameras and basic sensors, became a blueprint for future Marscopters, including a heavier Dragonfly mission destined for Titan's methane skies. Even its communication system offered lessons. Relying on Perseverance as a relay station showed how networked robotics could work in concert across alien landscapes. Perhaps the most poignant triumph was watching Ingenuity adapt to adversity. When dust storms coated its solar panels, engineers remotely tweaked flight schedules to maximize charging. After a navigation glitch forced an emergency landing in 2022, the team rewrote its software mid-mission, teaching the helicopter to recognize hazardous terrain on the fly. These weren't just troubleshooting exercises, they were glimpses of a future where robotic explorers think independently, navigating worlds too hostile for human oversight. When Ingenuity's final flight ended with a broken rotor in January 2024, it wasn't a failure, it was a mic drop. This shoebox-sized pioneer had flown 50 times farther than planned, proving that even in the harshest environments, Ingenuity lives up to its name. Its legacy lingers in every blueprint for off-world aircraft, in every scientist who now considers the sky as part of their toolkit, and in the quiet patch of Mars where a tiny helicopter rests, not as scrap metal, but as a monument to the moment we taught the stars how to dance. After 7 years and 4 billion miles of interplanetary travel, a charred capsule no larger than a truck tire streaked across the pre-dawn sky of Utah's desert on September 24, 2023. Inside lay something priceless, a handful of dust and pebbles scraped from the surface of Bennu, a carbon-rich asteroid that could hold secrets to life's origins and Earth's eventual salvation. The OSIRIS-REx mission's triumphant return wasn't just a technical marvel. It was a time machine delivering raw materials from the solar system's birth and a dry run for the day we might need to deflect a world-ending rock. The journey to Bennu reads like an astronaut's fever dream. Arriving in 2018, OSIRIS-REx spent 2 years mapping the asteroid's treacherous surface, a rubble pile where mountains of debris shifted under microgravity. Scientists gasped when images revealed Bennu wasn't the smooth, sandy beach they expected, but a jagged nightmare littered with car-sized boulders. The original plan to scoop material with a robotic arm had to be scrapped. Instead, engineers devised a daring touch-and-go maneuver nicknamed the KISS. In October 2020, the spacecraft descended at walking speed, blasted Bennu's surface with nitrogen gas to stir up debris, and captured the swirling material in a collector head for just 6 seconds, long enough to accidentally overfill it so violently that precious particles jammed the lid open. Those escaping crumbs became a bittersweet victory. While mission controllers scrambled to secure the sample, they confirmed at least 400 grams had been collected, far surpassing the 60-gram minimum. The overflow provided an accidental bonus. Scattered particles allowed instruments to analyze Bennu's composition in real time, revealing startling concentrations of water-bearing clays and organic molecules like glycine, the simplest amino acid. These findings suggest Bennu might be a fragment of an ancient ocean world, delivering chemical precursors for life to Earth billions of years ago via similar asteroid impacts. But OSIRIS-REx's most urgent lessons concern planetary defense. Bennu is classified as a potentially hazardous object with a 1 in 2,700 chance of impacting Earth in the late 22nd century. During its close study, the spacecraft discovered something unnerving. Sunlight itself was altering Bennu's orbit through the Yarkovsky effect, a subtle push caused when asteroids absorb warmth and re-radiate it as heat. This phenomenon, barely detectable from Earth, could be the difference between a near miss and a catastrophe. By measuring Bennu's thermal properties up close, scientists gained a blueprint for predicting and one day deflecting such threats. The sample's analysis is rewriting textbooks grain by grain. Early peaks inside the canister revealed glittering serpentine minerals that only form in water-rich environments, hinting at Bennu's soggy past. Tiny iron sulfides spotted in the material could explain how asteroids concentrate rare metals, a clue for future space miners. But the real treasure lies in the pristine carbon compounds, untainted by Earth's atmosphere, that may hold recipes for life's earliest chemistry. What makes this mission extraordinary isn't just the science, it's the symbolism. That Utah landing marked humanity's first successful asteroid sample return, proving we can reach out, touch the cosmos, and bring pieces home to decipher. As labs worldwide begin dissecting these cosmic crumbs, they're not just studying an asteroid. They're holding a piece of the story that might explain why we're here and rehearsing the maneuvers that could ensure we stay. On the far side of the moon, where Earth is never visible and radio silence reigns, a robotic pioneer made history in January 2019. China's Chang'e 4 lander didn't just touch down in the unexplored expanse, it cracked open a window to the solar system's most ancient secrets. Unlike every lunar mission before it, Chang'e 4's landing site, the von Karman crater within the South Pole Aitken Basin, was chosen not for ease of access, but for its geological time capsule status. This 1,300-mile-wide impact zone, one of the oldest and deepest in the solar system, exposes material from the Moon's mantle that was blasted upward during a cataclysmic collision over 4 billion years ago. The real genius of this mission wasn't just the landing, it was the celestial dance that made communication possible. Since the Moon's far side always faces away from Earth, direct radio contact is impossible. Enter Queqiao, the Magpie Bridge relay satellite. Parked in a halo orbit 60,000 kilometers beyond the Moon, this technological linchpin uses gravitational equilibrium at the Earth-Moon Lagrange point 2 to bounce signals between Chang'e 4 and ground control. Without Queqiao's steady hand, the lander's discoveries from subsurface radar scans to cosmic ray measurements would have remained locked in perpetual silence. What Chang'e 4 found beneath its treads rewrote lunar geology textbooks. The Yutu-2 rover's ground-penetrating radar revealed layered structures suggesting the basin was filled by multiple waves of molten rock after its formation. A puzzle for theorists who assumed single massive impacts left simple bowls. Spectrometers sniffed olivine and low-calcium pyroxene in the soil, minerals that likely originated deep in the lunar mantle. These findings support the Big Whack theory that the Moon formed from debris after a Mars-sized object collided with the young Earth, but they also hint at a more complex volcanic history than models predicted. The mission's quietest revolution might be its biological experiment, a sealed biosphere canister containing cotton seeds, potato sprouts, and fruit fly eggs briefly sprouted greenery in the low-gravity, high-radiation environment, marking the first time life grew, however briefly, on another world. Though the seedlings froze during the 2-week lunar night, the proof of concept could shape future Moon base agriculture. Chang'e 4's endurance stunned engineers. Designed for 12 lunar days, about 3 Earth months, the lander and Yutu-2 rover were still returning day to 3 years later, having survived temperature swings from 270 degrees Fahrenheit at noon to -290 at night. Their longevity turned a symbolic first into an unrivaled scientific haul, from mapping neutron radiation variations to capturing the first clear radio astronomy observations from the Moon's electromagnetically quiet far side. This mission's legacy isn't just in the rocks it analyzed, but the barriers it broke. By proving sustained far-side operations possible, China opened the door for future radio telescopes shielded from Earth's noise, or even sample return missions targeting the mantle chunks that could reveal how rocky planets differentiate. While flags and footprints dominate lunar nostalgia, Chang'e 4 reminds us that the Moon's greatest gifts may lie in its scars, the violent records of a time when the solar system was still carving its identity in fire and stone. Beneath the cracked ice shells of Europa and Enceladus, entire oceans churn in perpetual darkness, vast liquid expanses that could harbor secret science has chased for centuries. These aren't the frozen wastelands they appear to be from space. Europa, Jupiter's 4th largest moon, hides a subsurface sea twice the volume of Earth's oceans under an ice crust up to 15 miles thick. Enceladus, Saturn's tiny wonder, sprays its hidden ocean into space through geysers near its south pole, creating one of the solar system's most dazzling spectacles. What makes these moons so tantalizing isn't just the presence of water. It's the trifecta of conditions scientists consider essential for life: liquid water, chemical building blocks, and energy sources like hydrothermal vents. NASA Europa Clipper, set to launch in 2024, represents humanity's most ambitious attempt yet to probe these alien seas. Unlike landers, this spacecraft will conduct 45 close flybys, skimming as low as 16 miles above Europa's surface. Its ice-penetrating radar will map the thickness of the icy shell, while a thermal imager hunts for chaos terrain, regions where warmer water might rise close enough to the surface to create telltale cracks. But the real game-changer is its mass spectrometer. designed to sniff out organic molecules in the Moon's tenuous atmosphere or plume material. Imagine detecting amino acids or lipids in a passing geyser's spray, chemistry's quiet whispers suggesting we're not alone. Meanwhile, Enceladus has already served us samples on a silver platter. Cassini's daring plunge through its plumes in 2015 revealed hydrogen, carbon dioxide, and even silica nanoparticles, evidence of hydrothermal activity on the seafloor. Future concepts like the Enceladus Orbolander would take this investigation further, orbiting to analyze plumes before landing near active vents to drill through surface ice. The technical hurdles are formidable. Drills must operate in -200°F temps, while instruments endure saltwater corrosion. But the payoff could redefine biology. If life exists there, it might resemble Earth's extremophiles, organisms like Pacific vent worms that thrive without sunlight, metabolizing chemicals from hot springs. Dragonfly NASA's rotorcraft mission to Titan may seem like an odd player in this search, but Saturn's largest moon offers a different flavor of potential biology. While not an ocean moon, Titan's methane lakes and organic-rich atmosphere simulate Earth's probiotic chemistry in deep freeze. Dragonfly's 8 rotors will carry it between sites where it can analyze complex molecules forming in Titan's frigid dunes. What we learn there could illuminate how life's precursors assemble even in non-water solvents, expanding the very definition of habitable environments. The philosophical implications are staggering. Confirming microbial life on these moons wouldn't just answer whether we're alone. It would suggest life arises readily given the right ingredients, peppering the cosmos with infinite variations. Conversely, finding sterile oceans would force a reckoning. Is Earth's biology a fluke? Either way, these missions represent a pivot in exploration, from mapping landscapes to hunting for neighbors. As Europa Clipper's solar arrays deploy and Dragonfly's rotors spin up, we're not just sending machines, we're casting fishing lines into the cosmic deep, hoping anything tugs back. From the first artificial beep of Sputnik echoing across the Cold War to the James Webb Telescope peering back toward the dawn of time, these 30 events didn't just mark milestones, they rewrote humanity's relationship with the cosmos. Each breakthrough shattered ceilings of possibility, turning science fiction into textbooks, transforming geopolitical rivals into collaborators, and proving that the universe is far stranger, grander, and more accessible than our ancestors dared dream. Consider how profoundly our daily lives are shaped by these leaps: GPS guiding ambulances, weather satellites predicting storms, medical imaging derived from space telescope tech, all spun from ambitions that once seemed as fantastical as stars themselves. But the true legacy isn't just in gadgets or headlines. It's in the psychological shift these moments engineered. Apollo's Earthrise photo awakened environmental consciousness. Hubble's deep field humbled us with galaxies numbering in the trillions. Gravitational waves turned space-time into a symphony we could finally hear. Collectively, they've rendered the universe less a distant stage and more a shared neighborhood, one where water flows on Mars, black holes fling stars like marbles, and robots doodle helicopter tracks in rusty alien dust. Yet for all we've uncovered, the horizon stretches infinitely wider. The next century promises city-sized telescopes peering at exoplanet continents, fusion rockets slashing travel time to Mars, and perhaps the ultimate revelation, evidence that life thrives beyond Earth. This isn't passive spectacle, it's a call to participate. Whether you're a student sketching rocket designs, a citizen scientist classifying galaxies, or simply someone who pauses to watch a launch livestream, you're part of this story. The greatest lesson of these 30 events: that exploration isn't a checklist completed by a select few, but a perpetual conversation inviting every voice. So stay restless. The next chapter waits in icy plumes spewing from Enceladus, in quantum probes testing warp drive theories, in the stubborn static of a radio signal not yet decoded. The universe has whispered 30 answers and a million new questions. Our job isn't just to listen, but to lean forward and whisper back.